So in our previous class, we have seen the basic data types, variables, and data structures in Python. Let's look into the in-depth of these data structures, and also we'll take a brief introduction to the classes in today's class. So from here, I'll open a new terminal in my VS Code. So if I want to go into the Python shell, I can do it through this command, Python, and now I'm in Python shell. So yesterday we stopped in while discussing about the classes. So to work with object-oriented programming, we make use of classes. So why do we need object-oriented programming? First of all, so if you think of our code that we have written so far, it's all procedural, meaning do this, do this, do this, do this. And while that is okay, and for us humans, it makes more intuitive sense to think of objects. Let's say in real world, we have objects and their properties and their actions. So what we perform on those objects, any kind of object has a set of properties and a set of functionalities. So if we think in these terms, it makes more sense to have objects, think in terms of objects rather than uh, a set of tasks that need to be done. So that's why object-oriented programming came into existence. So for defining a specific object, we have to have a template of that object. Let's say a pen has an ink, has a refill, has a cap, has a body of it. These are all the attributes, and its function is writing. So if I do write, that is an action performed on the object. So to define these set of attributes and its set of actions, we make use of classes. Class is a template of an object. So I will define a class, for example, here, and I'll explain each of those things. For defining a class, we need to use the keyword class. So I'm going to describe the dog object. It's an animal, but of course, if we think of it as an object, that makes more intuitive sense. So every class in Python should start with a capital letter. So I'll use capital T, dog. So this is how I defined a class. So class, if I have to add some attributes inside this dog object, dog class, I need to add those in a definition. So now we have defined a class object called dog, and there is a default function called init for every class object. So I have to define or override that object, that function, like this, def 2 underscores init, and then 2 underscores. And then this is actually a function, but when it comes to object-oriented programming, within a class, if I define a function, it is called a method. So init is actually a constructor method. So I will explain what a constructor is in a bit. Let's define this method. So every class method will have a default argument passed into it, which is called self. Basically, it will pass the object itself. So when I'm defining an object, the object reference is what is passed into this self variable. So I'll explain more into this self variable in a bit. So once I have this defined in the body of it, I can initialize all the attributes of a dog. So a dog has 4 legs, a dog has a name, and so on. Let's say I will do self. To define a property or an attribute, I need to use self and dot any property name. Name of the dog, I'll just initialize it with Rex. And then I will have another attribute called legs. So it's an integer. Let's do self dot color as black. And that's the end of the constructor method. And let's say these are all the attributes. So let's say, what does it talk to? It eats, it barks, all that. Let's define that action also in this. So define one more method saying speak. This also accepts an argument. All methods accept the default argument if you're not passing anything. Speak. So what it has to do, let's say when I say the dog is speaking, I'll just write something like bark. So this is what we defined. So this object template or a class has a set of properties, name, legs, color, and then it has a function or action it can perform, which is speaking. And this is template is defined. So now I want to create a dog object. So I need to initialize this dog object. So do it with my dog, just like lists and integers or any kind of variable, we can define a variable and then initialize it with a dog object. So in order to construct a dog object, I need to call the constructor like this. What this actually does is it will call this function inside this class that will initialize an object with name rex, lex4, color black, and returns that object into this variable. Now, if I print my dog, this is a class object. This is an object. So if I want to print my dog dot color, it will print that it's black. Name rex. Rex it has 4. Now if I want to do some operation on this, I can do that. It has an operation called speak, and I'll call that, and it printed bar. So let's say I want to create one more dog. I will create a dog, one more dog, same thing. Print one more dog dot name. This also has the same name. So I want to make this name configurable. So if I'm creating a dog object, I want to pass a name to it, and all that color also I want to pass it, and initialize that object with that kind of properties or attributes. So in order to do that, we need to modify the constructor. Let's redefine the constructor here. Going back to the class, here I'm going to add one more argument called name here. So I'm going to use that name argument in the constructor. And then I will also use color. And one interesting property of one interesting aspect of Python I want to discuss here. We can also specify default values for these properties. If I'm not passing any values to it, we can define the default properties. So the default property for color, I'm going to use as black. Default value of color, I'm using as black. And default value of name, I'm going to use as rex. So if I'm not passing these two values, variables, or the arguments, it will by default assign name as rex and color as black. Let's define this, and now dog1, dog of name, I'll give Lucy, color as white, and dog2, I'm going to not use anything. By default, it will be Rex and black. Let's print dog1 dot color, print dog2 dot color, dog1 dot name, dog2 dot name, dog1 dot name. It's all defined. And when I do dog2 dot speak, it does the same thing. Dog1 dot speak, it does the same thing. I can do some set of modifications here and print the details of a dog, of the dog. Self dot name, I can access this variable, says going to define initialize dog value, dog1 as Lucy, dog2 as dog. Now I'll just do dog1 dot speak. Lucy says bark. Dog2 dot speak. Rex says bark. So this is how we use objects in Python. We'll go in depth into objects in a bit, but before that, we have already seen the basic data types and data structures. We didn't see how to manipulate these complex data structures yet. So let's do that now. So before we dive into this, let's do a simple exercise for defining a factorial function. So I'm going to define a function called factorial. What it does, given a number, I'm giving a number, and it returns the factorial of the function. Given n, variable n, it returns n factorial. So if you have seen mathematics, n factorial is like n into n minus 1 into n minus 2 into and so on till it reaches 1. Let's say 5 factorial actually means 5 into 4 into 3 into 2 to 1. 5 factorial is this. So I want to do that programmatically now. So I will pass factorial of 5, and it should give me the actual value of factorial of 5. For that, we need to do something like this. If the number n is equal to 0, it should return 1. So factorial of 0 is 1. So factorial of 1 would be like 1 itself. So we can do it in 2 ways. One way is to write some logic. Because before we even do the logic, we need to check if the type of n is number or not. If type of n is not equal to integer, return none. And if it is a negative number, we don't have a factorial. If n is less than minus 1 or n is less than 0, return none. So for these 2 cases, we are not going to calculate. It's an error handling scenario. If n is 0, we have to pass in 1. So first approach we'll define a variable called factorial. We'll go into this later. Right now, let's just define factorial value as 1. So because for 0, it will be 1. Okay. And for 1 also, it will be 1. So I will just count a value. Counter 1. While count number is, so I'm actually going to go from 1 to up to the number and multiply all of them and then sum it up into this factorial, add it up into factorial. So I'm going in the reverse order. Instead of going from 5 into 4 into 3 into 2 into 1, I'm just going the reverse order. 1 to 5, 1, 2, 3, 4, 5. I'm just doing 1 into 2 into 3 into like this. So counter, I'm initializing it to 1 because it starts from 1. And while it is less than or equal to the number, it has to go till number 5. If I'm taking an example of 5 as the factorial number passed, while count is less than or equal to n, and multiply the counter factorial equals factorial into count. And then count, I need to increment. So every time I iterate through this loop, I need to increment by 1, which is 1. First time it should 1 into 1 it should do. And second time the previous value into 2 it should do. And previous next iteration it has to 3 into 3 and so on. What it results in now is first thing, the first iteration, the factorial will be 1. 1 into the count is 1. So it's still 1. Next iteration, count is going to be incremented to 2. That time, the previous value of factorial is, let's go through this iteration by iteration. 1 equals 1 into 1. This is the first iteration, and count was 1. Count is 1. Now, factorial also is 1. So this will become like this. Next, count will become 2. And previous value of factorial is 1 equals 1 into this count value, which is 2. Now the factorial becomes 2. After this also factorial becomes 1. This is the factorial value. And then next iteration, initial value is 2. Now count becomes 3. Next iteration. Every iteration we are actually increasing the value of count by 1. This is the first iteration. This is the second iteration. This is the first iteration. This is the second iteration. This is the third iteration. Previous value of factorial is 2 equals 2 into count 3. Now factorial becomes this one factorial. This one will become factorial. Let's repeat myself. This is the first iteration. So count is actually 1. Factorial equal to factorial value, initial value is 1 into count is 1. Okay, now count will become 2 because count equals count plus 1 we are doing. This is first iteration. Second iteration, count is already 2. Now factorial becomes, what is the value of the factorial in the previous iteration is 1. Right? This result of this thing is 1 into 1 is 1. So the factorial is actually 1. Value of it is 1. So value of factorial in the previous iteration was 1, and now I'm going to use count again according to this logic. Count value is 2. That time value becomes 2. And third, and also now I'll increment the counter by 1. Now it becomes 3, and third iteration continues. Factorial equal to previous value of factorial is 2, and the count value is 3, and now the value becomes 6. Count will be incremented to 4. Fourth iteration, factorial equals previous value of factorial is 6 into current value of counter is 4. Now the value becomes 24. Like this, it continues till the count becomes 5. So now this count becomes 5. And why we have put the condition as less than or equal to. So even when the count is 5, it will run one more time. This will be the last time it will run this loop. So that time it will calculate fifth iteration. Factorial becomes the previous value, which is 24. Current value of counter is 5. This will become the value 24 to 5, 120. So instead of writing all this, this is a representation that I have given explanation. I can just comment on this part and run this code directly. So what this loop is doing this operations one by one in every loop. And after the end of the loop, I'm going to return a value called factorial. I'll call this code. And then now run this code. Python. PyScript.py. I run this. I haven't printed anything here. So I just print the factorial of 5. Factorial of 5 is string of factorial of 5. Is 120. Let's use 6 instead. So 6 is 720. No, particular 7 is 5046. Okay, this is one way to do it. There is even a better way to do this. Let's use another approach. I'll define a more function factorial 5. Similar to this, we have to check this conditions. If type of, I think we should use the number. I'll just use the value variable name as none. If type of number is not equal to integer, then return none. This is handling the negative scenarios. If number is less than 0, return none. Now we're going to handle a situation where the number is 0. If number is equal to 0, return 1. If number not equal to 0, then what we want to do is, so if we think logically, so 5 factorial is actually going to be 5 into 4 factorial. And 4 factorial is going to be 4 into 3 factorial. So in general, n factorial is equal to n into n minus 1 factorial. So this logic is what we are going to use in this. So now I have number n. So I need to find out the factorial of n minus 1 factorial, n into n minus 1 number into number minus 1 factorial. Right. That's what I'm going to do here. Return number into this factorial we already defined. This is called a recursion. So we will find the factorial of number minus 1. So this function is actually calling itself again with a new number. So this is an iterative way of implementing this logic. So 5 factorial will become 5 into factorial of 5 minus 1, which is 4. So every time this returns the 4 factorial value. And it will multiply 4 factorial by 5, which is essentially the 5 factorial. Let's do the same, execute the same thing with this function. Just remove this. Seven factorial is 5040. Same thing. Let's try with 6. And then 5. It's the same implementation, but it's a different way of implementing this in a recursive format. So this also can be done, and this is more optimized. So I'll move this 5 to factorial. Okay, that's about a simple implementation of a factorial. So now let's go back to Python and discuss about the data types, in depth into the data types. So we have seen division operation in our previous class. 20 divided by 4 is actually going to give us a real number, 5.0, which is a floating point number. Let's do some arithmetic on floating point and integer. So these both are integers, it's not floating point numbers. But division operation is always giving us a floating point number. So what if I do operation on one integer and one floating point number? It gives a floating point number. So compared to integers, floating point numbers are a bigger entity. We store larger values in floating point numbers. Always when we do some operation on a bigger value entity, the interpreter will convert the lower value entity into the bigger value entity. Integers also will get converted into floating point numbers if I am doing addition or any operation with floating point numbers. That's a logic here. So same thing applies to even multiplication, even exponential operations. 4.0 as an exponent if I do, it becomes a floating point number. So I can actually convert this into integer. Let's do that. How do I do that? Is through this. 4 power 4.0 to 56 integer portion it is extracting and showing here. It's again converting into integer. 45 to 8.9. It's not actually rounding this, but it's eliminating the decimal part of it. It's only giving the real part of it. The decimal portion it is removing entirely. Integer. This is called typecasting in Python. In any language, we call it as typecasting. So one type of variable is value is being converted into another type. What if we do 8.99999? So on. It's almost 9. It's not going to round that value. It's going to eliminate the decimal portion and gives only the real portion of it. Similar to this, if I have 14 by 3, it gives only the integer portion of it. So if I actually do 14 divided by 3, it's actually a regression, repetition of 6666 and so on. It's at the end, it is approximating it to 67. That's the precision level that the system supports right now. So what if I want to round this value into a higher one, which is like almost near? If it is 8.3, it should go to 8. If it's 8.9, it should go to 9, something like that. So if I do round operation on 14 divided by 3, it gives 5 because 4.6 is actually greater than 4.5. So round operation will approximate it to the next integer, which is the nearest integer. It will do that. It will convert that. Okay. Coming to the floating point discussion, let's do some simple calculation. 1.2 minus 1.0. What should this actually be? It should be 0.2, right? But it is giving this number. This is called floating point error in computation. You can do research on how these floating point numbers computation matters and how it's going to affect the calculations. So our computers only represent floating point numbers as approximations. So it will first convert a number into a mathematical scientific representation and represents that in an exponential format. So actually, if I'm storing a floating point number called 0.2 or 1.2L, let's just take the example of 12.5. So how the system stores 12.5 in memory is first it will convert that into scientific notation. So the binary equivalent of 12.5 is going to be 1100.1. So how did I come up with this number? So if I divide 12 by 2, the remainder. So how to convert a whole number, integer then base 10 integer into a binary number. So these things we divide by 2 every time and make the remainder as the value. So I will show you these calculations later, if how to do that. And the ones that are on the right side of the dot are going to be multiplied by 2. So if I multiply 0.5 by into 2, it will become 1.0. So that's why 1 will become 1. So the binary representation of this will be 1100.1. So this is a multiplied. If I want to convert this part of it, I need to divide by 2 and add the remainder here. If I have to convert the right side portion of the floating point number, I have to multiply by 2. 0.5 into 2 is 1. So that will become here. So these are all not necessary. Just to give you the background of how these floating point errors happen, it's just enough to know that floating point errors happen. And this is the floating point numbers are just approximations to the nearest value in exponents. So first, system will convert this into a scientific notation called 1, something similar to this 1.1001. So all scientific numbers start with 1 point something into 2 power 3. If this is confusing, just bear with me. It's not important, but just giving you the background of why these floating point numbers don't have exact values. This gets stored in the memory. The real portion of it will be stored in one place, and the exponent, which is 2 power 3, is stored in one place. So all of them cannot be represented exactly. That's the reason it happens. So for avoiding this kind of scenarios, we have another data type called precision, precision decimal. So for decimals, we need to use a library called decimals. So if I just do rounding of 1.2 minus 1.0, it gives the correct value. Round. Okay, I think let's do 1.2 minus 1.0. So because it is near to zero, it is giving the zero. If I want to round it according to a specific precision, let's say I want to approximate by 2 decimal points and do it this way. And it approximated to 2 decimal points, 0.2. Let's convert integer 100 now. See how this works. And this actually is converting string 100 into decimal integer 100. And I can represent the base of this. So this is actually base 10 number. If I consider this as base 2 number, what will be the value of it? So the integer has an advanced feature to represent a string and convert that into binary. So we have converted this. Previously, we have converted this into binary, right? When we are showing how these floating point numbers are represented. In order to convert number 12.5, we had come up with 1100.1. So how do I convert that? Yes, through this. If I have a string in it, I can convert by base 16 or base 2 or base 10. By default, it is base 10. If I convert this string into base 10 value of decimal number, it is 100. If I make it as base 2, the value of it is 4 because 2 power 0, 2 power 1, 2 power 2. 2 power 2 is 4. So similarly, we can also convert numbers that are represented in hexadecimal format, base 16 format also into this. So base 16 is about base 16 numbers start from 0 to up to 16, 15. C, D. So these are base 16 numbers. So base 10 numbers start from 0 to 9. Base 16 numbers start from 0 and end at F. Base 2 numbers has only two values, 0 and 1. So here we are converting this 100 into base 10 number, which will result in the value 100. If I convert this 100 into binary and its value becomes 4. And if I convert this string into a hexadecimal value, its value is equivalent to 427. That's what it is. So now we have decimals, right? 1.2, and we can go back to the discussion about decimals. In order to approximate these or precision numbers, if I want to approximate, I can make use of a special library called decimal library. So for that, I'm going to import decimal library, import decimal, and there is another thing called get context. It's a method. I'll just explain you in a bit. So let's get the context first. So context has a specific precision value. Right now it is set to 28. So the precision is going to be 28 characters onto the right. So I can set the precision value with this get context dot precision. Say I will initialize it to 4. Now if I do decimal value, divided decimal value of 1 divided by decimal value of 3, it gives me 4 precisions. It gives me 4 values. By default it was 28. Now it is set to 4. This is an advanced data type. You don't have to understand it fully. Just that know that this is there. Let's just use math function, or by just do decimal of 0.14. This is actually stored as this. So just like I discussed earlier, it's an approximation of the value. It's not actually 3.14. The computer stores this floating point number as an approximated value. So that is about floating point numbers. If it's all confusing, just forget about that. Floating point numbers, just this is enough. Knowing that floating point numbers do not get stored exactly in the memory. It's just an approximation of nearest value. That's enough to know. So we already saw casting earlier. So integer of 1 we have seen. Similar to that, we can have casting on other data types. Let's say I will convert a value of 1 into Boolean. What will this result in? It results in true. So any non-negative number is a true value. If I do 0, it's 0. Even negative numbers will become true. So anything that is non-zero is a true. If it is 0, if a value is 0, it is false. Let's say I have a variable called a, which is initialized to 4. And if I do if a, print a, this actually evaluates to true. And if I initialize that back to 0, and if I do the same thing, it is false. If I initialize it to again -1 and print it, it's still going to be true. So any value that is not 0 is true value. Even complex numbers, if I do Boolean of 1j, even complex numbers are true values. Similar to that, if I have an empty list, this is going to be false. Any non-empty list will become true. And there is something called none type in Python. Let's see what that none type. None type is also false value. So in similar context, if I have a list called 1, 2, if my list, if I do print my list, my list will evaluate to true because the length of my list is not empty. It's not empty list. So let's just reinitialize this my list with an empty list. And if my list, and this is not getting executed because this is evaluating to false because it's an empty list. Similar to that, if I have A as 5, B as 5, A minus 5, A minus 5 is 5 minus 5, which is 0. Similarly, this also doesn't get executed. If it evaluates to 0, it always becomes a false statement. Instead of this, I can just do A equals B. This is equal to B. A is equal to B. Okay. Is this too confusing? Should we stop here or should we continue?
అర్థమవుతుంది సార్.
Okay. Okay. Next logic we have to look at is not logic. Let's just take an example of whether it is nice is a Boolean. Let's say it is false. I have an umbrella or not. I have an umbrella. Okay, true. I'm going to write some logic here. If I don't have umbrella, or if weather is nice, I'm going to stay inside. Else, I'll go for a walk. Is there anything wrong in this statement? So now it says if I don't have an umbrella or weather is nice, weather is if I don't have umbrella or weather is nice, that means I could actually be thinking that this not applies to both these. This could mean, like, initially, if I'm thinking like this, if I don't have umbrella or the weather is nice, this not applies to only this statement. It does not apply to this statement. So if I execute this, it's saying go for a walk. Weather is false. I have an umbrella. Let's just do one simple logic here. This not applies only to, so this is actually similar to not have umbrella, or if I don't have umbrella or if weather is nice, stay inside. Else, go for a walk. If I don't have an umbrella or if the weather is nice, this should get executed. Have umbrella is true, so this becomes false, or weather is nice is also false. So this statement will not go in because this evaluates to false and this evaluates to false again. So false or false will become false totally. So this statement gets executed. Go for a walk. If I change one condition here, weather is nice is I'm just going to change have umbrella to false and weather is nice to true. What I want to do is if the weather is nice, I don't need an umbrella. So at that scenario, what this code behaves like, let's say it's still suggesting stay inside. So have umbrella. No, I don't have an umbrella, but the weather is nice. What this statement is evaluating is have umbrella false, it becomes true, or weather is nice. True or true, and it's going inside this. What I actually intended to do was if the weather is nice, if weather is not nice, then only I would need umbrella. If it is weather is nice, I don't need the umbrella to go outside. So to appropriately represent this in the code, I have to do either this, if not have umbrella, or weather is nice, stay inside. Else, so this actually applies, this not applies to both these. If I have umbrella or if I don't have an umbrella or if the weather is not nice, stay inside. Otherwise, I can go for a walk. So, but this again, have umbrella, false, weather is nice. Weather is nice is true, so it's suggesting go for a walk. So what I'm trying to say here is this not is only going to apply to the first next immediate item, not to the entire set in the if condition. If I have to write it to apply to both statements, if not umbrella and not weather is nice, stay inside. Else, so this should be written like this. So the idea here is the not applies only to the next immediate item, not to the entire set. So after the and, if I have to negate this, I have to use not again. So this statement, I can write it in a better format. That's just, it's more clear that way. If I have umbrella, or if the weather is nice, no matter what the weather is, if I have the umbrella, I can always go for a walk. If I don't have an umbrella, this becomes false. And if weather is nice, it's enough to go for a walk. I don't need an umbrella. Else, this becomes stay indoors. So I have an umbrella. Weather is nice. I just change the conditions. Have umbrella. False. Weather is nice. False. Both are false. Now I'm going to run this. Stay. It's suggesting stay. I don't have an umbrella, and I don't have weather as nice. Now I'll change the weather is nice to true. Now I can go for a walk. I'll change back weather is nice to false and have umbrella to true. Now I can go for a walk. Even though weather is not nice, I can go for a 1 because I have the option. That's how these logics work. The point here is the not applies only to the immediate next item, not to the entire conditions that we put in the if condition. And there's one concept we need to cover in lists. Let's say I have a list of names, or I can just have a name. My name is Matish. So if I want to access a specific character, I can access through the index. Name of 0 will give me M. Name of 1 will give me the next immediate item. And if I want to access a range of characters, I can do it through 0, starting index 0 and ending index 7, but not including 7. So it will go till 0 to 6. My name is getting listed here. Similar to this, I can actually, if I'm starting with 0, I can actually eliminate the first item itself. If I just use name :7, it goes up to 7th index, but not including the 7th index. It gives me that. So if I want to list by from the 11th index to the end of the string, I can use it this way. Starting at 11th index to the end, it's giving this name. If you count the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, starting at 11. So this applies to strings as well as for lists. Similar to strings, I can have a list of numbers 1, 2, 3, 4, 5. I can do the same thing. My list of 2 to 4, it gives 2, index 2 and index 3. It'll not include index 4 because that's how it works. So index 3 and index 4, index 2 and index 3, it will give 0, 1, 2, and 3. Third and second and third index it gave, fourth index it won't include because it's 1 less than this number is what will be returned. And similarly, I can have length function for name, like this is 18 characters in length. And next we need to visit how to do formatting of strings. Let's say I want to have my number is, let's say, string 5. This is how we append strings or format strings. This is one way to append strings. There is a new format in Python that is introduced in 3.16, 6 I guess, 3.6 version. So there is called, these are called F strings. I can include numbers in the string itself. So I have defined a variable, or I'm defining the string like this. F strings are defined like starting with F and then single quotes or double quotes, both are accepted. So I'll just use my number is within flower brackets. I can use 5. Within this, I can actually have some kind of Python function or Python operations also. 5 into 5. This actually does Python calculations and stores that in the string. I can do the same thing with format also. There is something called py in math. It's a import math function. Math.py, I'll tell pi value is 3.14. Let me use this pi value in a string, formatted string. Pi is math.py. This is nice. So I can also do formatting. If I just want to print only the first two decimal values, I can do it with colon dot 2f, gives me only this two decimal values, 0.14. Similar to this, we can also do one more formatting. So pi means this dot format and dot pi. This also does the same thing. So next thing is to, if I have multiple lines of string, if I just initialize a value to this one, and I want to enter multiple lines of text in a single value or variable, I can't do it with this format with single quotes. So to define multi-line strings, I need to use triple quotes. Is one, is two, is three. I'm actually entering multiple lines here. This is multi-line. And how do I close the string is again three quotes. Now, if I just print A, it gives this. This is actually backslash n actually means it's a new line. So if I do print of A, it will print multiple lines. This is what the string contains, multiple lines. If I represent in Python format, it is going to be having backslash n characters. These characters mean new line characters. This is how we define multi-line strings. What if I have to use quotations inside a multi-line string? Let's say I have a is one having multi string with quotations. But if I want to use quotations again, I have to use backslash to escape the quotations. And then in order to close the string, I need to use three quotes again. And if I do print A, this has three quotes inside the string. Similar to this, I can have three double quotes. If I'm using double quotes inside single quoted strings, I don't have to escape them. So vice versa. Even this requires single quotes because this will evaluate to empty strings. I need to still use back quotes if I'm using multi-line, multiple quotes inside a string. So I print A now. It's the same as defining with single quotes. So that's about the strings, multi-line strings, and there is some data type called bytes.